Good day, this is Professor Will, CBMD, PhD, and today's Friday, November 19th, 2021. It is 5:32 and 13 seconds, a.m. Eastern Standard Time. And today's research, a bit of physics in the quantum world. So let's hop to it here. The physicists reveal non-reciprocal flow around the quantum world. Date November 16, 2021. Source, University of Exeter. The physicists have created a theory describing how non-reciprocity can be induced at the quantum level, paving the way for non-reciprocal transport in the next generation of nanotechnology. The researchers have developed a quantum theory explaining how to engineer non-reciprocal flows of quantum light and matter. The research may be important for the creation of quantum technologies, which require the directional transfer of energy and information at small scales. Reciprocity, going the same way backward as forward, is a ubiquitous concept in physics. A famous example may be found in Newton's law. For every action, there is an equal and opposite reaction. The breakdown of such a powerful notion as reciprocity in any area of physics, from mechanics to optics to electromagnetism, is typically associated with surprises which can be exploited for technological application. For example, a non-reciprocal electric diode allows current to pass in forwards but not backwards, and forms a building block of the microelectronics industry. The researchers provide a quantum theory of non-reciprocal transport around a triangular cluster and strongly interacting quantum objects. Inspired by the physics of quantum rings, they show that by engineering an artificial magnetic field, one may tune the direction of the energy flow around the cluster. The theory accounts for strong particle interactions, such that directionality appears at the sway of energies, and considers the pernicious effect of dissipation for the formation of non-reciprocal quantum currents. The research may be useful in the development of quantum devices requiring efficient directional transportation, as well as for further studies of strongly interacting quantum phases, synthetic magnetic fields, and quantum simulators. The research calculations provide insight into how one might instigate directional transport in closed nanoscopic lattices of atoms and photons with strong interactions, which may lead to the development of novel devices of a highly directional character. Good day, this is Professor Will, CBMD, PhD, on advanced physics, space science, and neuroinformatics. This video was created for educational purposes only. Hope you enjoyed listening. Until next time, have a great day.